Welcome to Breadboarding. This is video 22 in the Breadboard 8088 PC series, and in this video we'll be looking at what makes a micro IBM PC compatible. So in the introduction videos I outlined what I'm trying to do here with making a breadboard PC. It's going to be an Intel 8088 PCXT hybrid, and by that what I mean is we're going to be taking parts from the early PCs dating back from the 1981 PC, then the PCXT, AT, PS2, and then finally the compact Despro 386. So trying to run an early version of MS-DOS, probably 3.3 or even PC-DOS 2.11. We've already completed the monochrome display adapter earlier in the series of 9 videos. We've already added the clock CPU bus control and the basis of the ISA bus. But in order to make this project PC compatible, we're going to need to add direct memory access controller, timer, parallel port and speaker. We'll be adding a real-time clock, dual interrupt controllers, so we can add a mouse network cards in the future. And then we'll also be adding the PS2 keyboard, mouse, a high density floppy disk drive, and in the future phase we'll be looking at adding a CGA compatible color graphics controller, and we'll also be looking at adding an ID disk and disk controller. This is the block diagram that we've been developing over the last 21 videos. So we've got the system clock and reset clock circuit, the microprocessor, the buffers and latches for the data bus and the address bus controller, read-only memory, RAM and address decoder. Now that is pretty much generic across any microcomputer, wouldn't require these, but the bits which are not PC specific, which were more coming from the original Nanocom 6809 project, it's where we had the peripheral interface adapter, serial port and the 7-segment display and keypad, which provide us a simple monitor to be able to write programs and test things without having to run the full MS-DOS and BIOS. We then went on to create the monochrome display adapter video display, and this is entirely PC compatible. So this was the first step really on building our PC compatible breadboard PC. It is IO port compatible with the original MDA controller. We've added a few extra ports here for controlling the video palette, which is compatible with VGA output. So in our high level plan, I've changed the order of these a little bit in that as I was working through this, I was originally planning to do the PS2 keyboard controller. It became obvious when we looked at what other things we'd need, like interrupt controller, timer, power on self-test port, beep codes and things like that, and also BIOS, that really we need to do a few steps before we can really add the keyboard controller. So what do we need to make a microcomputer IBM PC compatible? We need to use the Intel 8086 compatible instruction set, and we're using the 8088. There were other manufacturers like NEC and AMD around this time that also produced compatible microprocessors. We also need to use a BIOS compatible with the IBM PC software interrupts. So this is the primary interface by which operating systems such as MS-DOS would talk to the underlying hardware. The IO ports and interrupts needed to be the same as the PC, or at least the BIOS needs to be configured for the differences. The system expansion bus, as IBM called it in the early days, or PC ISA 8-bit or 16-bit expansion bus, is also required. We do need an interrupt controller because this is needed for the way how the keyboard and floppy disk controller, for example, are integrated within the BIOS. Also, PC does rely on timers, some inputs on parallel port interface, port B, and the speaker is required for power on self-test beep codes. Then we need a direct memory access controller, and that's primarily required for the floppy disk controller and later the hard disk controller. There were some variants of the PC, such as the PC Junior and Tandy 1000, that didn't include a direct memory access controller, but that made floppy disk access a lot more complicated, and that was done for cost savings. We also need a PC compatible keyboard. So now let's take a look at the diagrams and things that we were looking at from the original technical reference guide. I've annotated quite a lot of these with information that we need to consider in building the later phases of this project. So in the overview diagram, a number of these parts we've already built out. So the CPU, oscillator, memory and ROM we've already done, but we still need to do the interrupt controllers, DMA, speaker, keyboard adapter. We're not going to worry about the expansion bus and expansion box. We've already developed the monochrome display adapter. We will be adding a diskette drive adapter, and we've already got a serial port there. And we will be adding the fixed disk drive adapter in the future. We're not going to worry too much about the game adapter at the moment, and in the next phase we'll also look at developing the color graphics adapter as well. So this diagram, the system board data flow, is important for understanding some aspects of the PCXT architecture. A number of these green bits we've already developed, so the clock generator, main processor, the address buffers, data buffers, bus controller, but a number of these other green ones we still need to add. Now the original PC had rather confusing bus setup. There was the main address and data bus, but there was also the X bus as it became known, and quite a lot of the components we're needing to add here were actually connected to the X bus, so that would be XA and XD. Although interestingly, virtually all of the control signals are actually coming from the X control bus and not from this other bus here. So in fact, virtually everything worked off the X control buffer, which is here. So the diagram's not 100% accurate. One of the complications of the X bus was that the expansion socket J8 needed special treatment. You can see down here that the J8 actually comes out here. Originally, there was some confusion about whether this was related to the expansion box that we looked at on the previous page. this expansion box and the extender and receiver card, in fact, there wasn't any requirement for these to actually be in the slot 8. So the slot 8 seemed to be a bit of an unusual thing just for the PC XT, and there don't seem to be really any definitive explanations of what it was all about. There were one or two cards that seemed to require special handling if they were put into slot 8, which we'll cover as we go through the explanation here. But what I'm proposing to do here is just going to make a single bus. I'm going to not use any of these buffers here, and the XA-XD bus are just going to be merged in with everything else, and we don't actually have to worry about slot 8. So the main thing coming out of here is we're going to be eliminating the X bus. We're going to get rid of a lot of the buffers and decoders that were needed for that. We're not going to bother with the non-maskable interrupt logic because we want to keep that for the moment so that we can still use our built-in monitor for debugging the monitor. So there's good background information on the bus architecture for the PCXT on -0degrees.net. This includes information on how the X bus works with the rest of the expansion slots and the motherboard RAM. In particular, the slot 8 required a special signal to allow the data flow to go back to here. Now, from what I understand, then even with following up with Sergey, there wasn't any great explanation of why slot 8 existed in this way. So I'm not going to worry about slot 8. We're going to get rid of the X bus altogether, and everything's just going to be running on the same bus. The ALS logic that I'm using is capable of driving more TTL inputs than the original LS logic that was used back in 1981-83 anyway. And then the address bus shows this a little more clearly. In particular, it's where the DMA controller is interfaced in with the system, in that the DMA controller kind of sits in the X bus and has a number of buffers and things going between the X bus and the main address bus, in particular the DMA page registers and the DMA latch for the A8 to A15 address range coming out of the DMA controller. But from what I can tell, there's actually no need to actually separate these two together, and in fact the DMA can operate quite happily just talking directly to the main address bus and data bus. There's no need for this XA and XD, so I'm going to eliminate it. So now I'm going to go through the 10 system board diagrams, and what I've done is where we've already added components and they're already installed and working, that is highlighted in green. Where we need to put new stuff in, I've done in purple, and where things are in red, then that generally means we don't need to worry about these things. So for the main system board, we've largely done this. The only issue we're going to need to do is add the programmable interrupt controllers. We're not bothering with the Matco processor. We are going to need to do a bit more to do with the timing, particularly for the DMA and the AN and AM board signals, which control a lot of the latches and things around DMA. So there's a bit more work we're going to need to do with that. And this input here is related to the control of DMA or the CPU accessing the bus. This stuff down here too, the non-maskable interrupt, I'm not going to bother with. Also the IO check, which is similar to parity checking for the IO bus, I'm not going to worry about because I'm not trying to get generic ISA cards to work with this. I'm just trying to get my own hardware to actually work with this breadboard solution. I'm not expecting it to work with any generic ISA bus card that's plugged in here. There's another bit here that the DMA clock, so the system clock, is not appropriate for use with the DMA controller. So the main system clock has a 3367 duty cycle. That doesn't satisfy the minimum high time needed by the DMA controller, so it is necessary to do something with the main system clock to make it compatible with the DMA controller. So it needs at least 80 nanoseconds high time, and by default I think it only has about 70 nanoseconds. So we're going to need to do something about that. We need to do some address decoding. These are all of the IO port decoding, and we're probably going to use one or more PLDs to actually do this. The rest of this here is all just to do with the dynamic RAM refresh. So DMA controller is one of the more complex aspects of this, and it uses the 8237 DMA controller. Again, the bits in orange here mean that we're just going to be talking to the main data bus and the main address bus. We're not going to be talking about the X bus. And that means we don't actually require this buffer here. There is a RAM chip here, which is a 4 bits by 4 address RAM, and this is used to provide the top 4 address lines, so A16 to A19, for the DMA requests. Now, the thing which is a little bit confusing here is the feed into the address lines for this for output only come from the DMA acknowledged 2 and DMA acknowledged 3, so these are active low. But I have got an excerpt from a book that I'll reference in the description below that actually explains how this works. Basically, when DAC 0 or DAC 1 are active, because these DAC 2 and DAC 3 will then be high, then address 3 will be enabled. Then when DAC 3 is low, then we'll have this address. And then when DAC 2 is low, then we'll get this address. Now, you can never have both of them low because only one of these can be active at a time. So it's rather confusing, and the explanation in the book that I'll reference, it actually explains a little bit better. So what it's basically doing is saying that the DAC 1 and DAC 0 share the same memory location, and because DAC 0 was originally used for the RAM refresh, this wasn't really a big issue. But it's a complication that has taken a little time to get to the bottom of. It's also further complicated that the power on self-test port of 8.0 also conflicts with that first location, which is never used. So this was one of the things that's taken me a number of hours hours to get to the bottom of. And it's all to do with the way how we're feeding these two DAC2 and DAC3 in as the address selections for this RAM here. And then there's another latch here that basically just takes the data bus and latches it for the A8 to A15. The DMA controller is only able to access 64K chunks of RAM at a time, and then it's necessary to break larger transfers into multiple calls to the DMA controller and to update the RAM address in here as well. So then the ROM we've already done, we don't really need to worry too much about that. The only other aspect here is that the outputs from the bus controller go through a buffer here and then join with the X control bus signals. But in fact, there's virtually nowhere in any of the diagrams where anything other than the X bus control signals are used. So in fact, the ones directly connected to the bus controller are very rarely used. It's all the X bus signals which are used. So the RAM parity multiplexers and buffers we don't have to worry about because we're only using one RAM chip that is static. Further RAM expansion we don't have to worry about. So this is the timer. So we are going to need a timer. You can see here that it uses the X bus control signals. We are going to be using this circuit here. We'll use one based on the XI8088, which doesn't require this chip, just uses a gate and a transistor. And the real-time clock that we'll be adding in a later phase is also going to be added here. There are some control signals here that we'll look at in a minute that we need for that. So this is one of the areas that needs the most changes. So the original XT keyboard made use of this LS322 shift register and used the port A 0 to 7 and a couple of other control signals as well. Because we're using a PS2 compatible controller, we don't need any of this aspect of it. And in fact, in Sergey's design, he replaced this 8255 PPI chip with just a couple of gates, and I'll be replacing this with a single transceiver latch, and we'll just be using port B and combining some of the other signals. A lot of port C was used for the configuration dip switch to allow the board to actually know what the configuration is. Now to start with, we're just going to hard code on that information into the BIOS, so I don't need it to be configurable. Then the expansion connectors, the power strip bus that we have is largely going to have most of this information. Things like the IRQs and the DMA lines will probably just wire directly into the breadboards with those, but we're certainly not going to worry about the X bus side of things. And this is just an example. The only schematic I could find that actually used slot 8, there's actually a jumper here that if it was plugged in, if this asynchronous adapter was plugged into slot 8, then it basically says that when we have IO read and the enable is selected, then it sets this signal on the B8 line of the ISA bus. So this was the only one I could find. So basically I'm not worrying about slot 8 at all. This is Sergey's XI8088 schematic, and what I'm doing is I'm going to be basing quite a lot of this stuff on his work that he's done, excellent work. And what we're going to need to be doing is adding some bus arbitration and wait logic. So the control for DMA does need some outputs from here. I'm not going to be worrying too much about the IO ready and the wait state stuff, but there are some signals here that actually determine whether or not DMA is going to be possible. We've also got the DMA controller information. Now there's one thing that Sergey's diagram here drives the DMA controller off P clock or peripheral clock, which is half the speed of the main system clock. I'm going to try and see if I can get the main system clock to be the right duty cycle, and I'm not going to use that particular one. Then got the dual interrupt controllers, so this is similar to the PCAT, so we're going to be using that. And this is where the port B non-maskable interrupt logic and speaker comes from. So we're going to be using the speaker. We're going to implement port B using 74LS 646, I think, which is a transceiver latch chip. Quite difficult to get, but I have actually got a number off eBay, and I'll be looking at using those. And this is basically just going to be port B with a number of signals. We're not going to worry about turbo, but there are some things like the timer outputs and the speaker gating and things like that, which will be handled in here. We're also going to be adding the timer, and the outputs here are then feeding into the gate over here. We've already covered the real-time clock, but we need to worry about the input-output select logic for that and also for port B. Then the one thing that I did notice here is in the keyboard controller that the A0 address line for the keyboard controller is actually connected to A2. I'll explain why that's important when we get on to some future slides, but there's quite a lot of the information here is very, very useful and will save an awful lot of time trying to work this out. So these are the hybrid breadboard issues. So slot 8 handling, not required, not going to implement it or worry about it. XBus for XD data and XA address, I'm not going to do. The power on self-test port 80 does conflict with the DMA page register for DMA 0, but DMA 0 page register is never used, so that's not really an issue. If we use the 8255 PPI port, then in fact port A would conflict with the keyboard controller. In fact, port A is used on the original XT for talking to the keyboard, but with the approach that Sergey's done, we're just implementing port B, then that shouldn't be an issue. And port B I'm just going to implement using one of these octal bus transceiver and register chips. And then the other step there is that because of the way how the addresses conflict there, we can't use the A0 line for the keyboard controller, because then that would conflict with port B. By connecting A2 to A0 here, then that means that the keyboard ports are then 6.0 and 6.4. And we'll see that in the BIOS, in fact, in Sergey's BIOS, he's already switched those ports so that the communications to the keyboard controller use port 60 and 64. We also need to do a consolidated I/O port and interrupt mapping, and that's going to involve consolidating information across the original PCXT, the XI8088, the compact Despro 386 and the PCAT, and also be using the Sergey's 8088 BIOS from GitHub here. So this is a consolidated I/O port and interrupt mapping. So the non-maskable interrupt we're not going to be using really for parity, but I'll keep it really for the nanocomp monitor abort. So this allows us to go back to the monitor whilst we're debugging things. The things in green we're going to implement, so the timer, the keyboard, the chained interrupt controller, so this allows us to have more than 8 interrupts. The serial ports I'm not going to worry about with too much at this point in time, neither the parallel, but the diskette controller we're definitely going to need to worry about. The real-time clock I'm going to add in later phrases, as with the mouse, and the fixed disk controller as well. But by adding these dual interrupt controllers, it allows us to have enough interrupts to be able to add everything that we want to do in the future. And then the I/O ports, we've got a DMA controller. We're not worrying about the second DMA controller for a moment. In the PCAT and upwards, then this one was for 8-bit transfers, the DMA2 was for 16-bit transfers. We've got both our first interrupt controller and the second interrupt controller, interval timer. The parallel port, we're only going to be implementing port B. The keyboard controller, as we said, we've mapped A0 to A2, so we're actually using these two ports and not conflicting with the PPI port. The DMA page register, we're only using 81, 82 and 83. 80, although there is a register entry for that, is never actually used by DMA0, and the power on self-test will actually use that. And in actual fact, the power on self-test, when it starts to boot the operating system, writes 0 in fact to the post. So in fact, the 80 in the DMA register would have 0 anyway at the time when we actually start the operating system. So things in red we're not worrying about. The fixed disk controller in orange will handle in the future. Just a note that the PCXT is a different I/O port, so we just need to be mindful of that to make sure that the software we're using is accessing it on the right port. The monochrome display adapter we've already completed and implemented. The only issue there is we've accessed the VGA palette in the first 4 addresses there, which are not normally mapped. We'll be adding the CGA adapter in a future phase of the project. We need to worry about the floppy disk controller, so we'll be adding that in this series of videos. And then we've still got the legacy nanocomp keypad and display and serial controller, which are in a much higher range. This means that we do need to make sure that we take into account the upper address lines for the I/O port, so this range does not conflict. So looking at the BIOS, there's a startup sequence in there, and what I've tried to do is to change the order that we're going to be building the project now to suit that. So we're looking at port B and the programmable timer, so we can get beep codes. We'll be adding a post register, power on self-test register, and the DMA controller. The programmable interrupt controller is also needed. We can see here that the order that things get initialized is the timer, the interrupt controller, then the keyboard controller, then working out the video mode and initializing the video. Then it initializes the real-time clock, then starts to look for the serial ports, the parallel ports, floppy disks, detect the RAM, and then test the RAM. If there's any extension ROMs, like in network adapters, then it will actually detect those and then run them. Then in the boot operating system, it first checks to see whether or not it needs to do any setup. So at the moment, until we have the real-time clock and CMOS, there won't be anything to do there. But once we have got the CMOS, we can configure the system configuration using that. Then it will attempt to load the boot sector from a floppy disk and start up the operating system such as MS-DOS. So this is the plan. So in the next couple of videos, we're going to be looking at adding the power on self-test port, the interrupt controller and the timer and the port B. This should allow us to get enough of the BIOS started to at least be able to get some beeps and to be able to see some sort of status information on the post port. So if you don't want to miss out on future videos, please hit subscribe, and if you found any of the content interesting or useful, please hit like. It just helps to make the videos available to more people. Thanks for watching.